So in this video, we're going to take a look at parametric equations. So imagine that you have a particle or object that starts somewhere. So say at time 0, it's right here, and then it moves. And maybe it moves on an interesting path like this. So at time 2, it's here, and then it ends up here. And essentially, this is how the path of this object is moved. And really the location, so say this location here, is a function for its x value, so in this direction at time t, and also there's a function for its y value. And so the point is being moved by both a change in the x and a change in the y. So the x value is being looked after by one function with respect to time, and the y value is being looked after by this other function with respect to time. Well, since each coordinate is a function itself, then we could just say, well, this overall location is x at time t, that's the x coordinate, and y at time t. So let's take a look at an actual example of this. So in this example, we're going to try and sketch x is equal to 2t minus 4, and the y is governed by 3 minus t squared. And the easiest thing to do is to make a table of values. And our table has a time column and a location for x and a location for y. And so we can just do little steps. Maybe what does this look like at all of these coordinates? And we can start to solve what values we get for x and y just by substituting them in. And then we just plot these points. So I now have coordinates. So I set up a small Cartesian plane. So at negative 8, which I didn't make a coordinate for, but it turns out it's at negative 8, 7 here, and then at negative 4 it's about here, and at 0 it's at 7. Oops, I guess that would be better if it was around the same height here. So this point. And so the path looks something like this. And it's important to show the direction of movement. So the direction is looking something like as shown by these arrows. Sometimes this is an awful lot like a parabola to me. And sometimes we can eliminate this, the parameter of the parametric and just write it as a function. And so we'll try that for this one. So we know that x is 2t minus 4, and we know that y is 3 plus t squared. So in this case, t would be x plus 4 all divided by 2, and y is 3 of these t's divided by 2 all squared. And solving this, we end up with y equals 1/4 x squared plus 2x plus 7, which is this parabola as well. It just doesn't tell you the parabola, the direction, how this particle or object is moving along this path with respect to time, because there's no time left because we've eliminated that parametric part of this equation. And in this case, you'll notice that we have parametrized a parabola. If you want to do this just with a line, it's possible to do as well, and there's a general formula for that. So a line can be parametrized by this. If you have a line through a point AB with a slope of m, then the x-coordinate will always be a plus some r value times t. The y value will always be b plus some s value times t, where t is going to be somewhere between infinity and negative infinity. And so basically for any r and s where r is not equal to 0, the slope will be S over R. And that works nicely if you have the slope. If you don't have the slope and you just have 2 points, say P and Q, then the X value will be A plus T value times C minus A. The Y value will be B plus T D minus B. And again, this will work on any time. So let's take a look at this through an example. We want to find the parametric equation for the line that goes through the point 3, -1 with slope of 4. So using the first equation, x is equal to 3 plus rt. The r value in this case is found in 1 second. Y equals -1 plus st, and yeah, s over r is our slope. So s is equal to 4r. And now you can just pick a value for r. So if I pick r as 1, then I automatically know that s is 4. So then I can go here and say, well, that's 1t, and this is y equals -1 plus 4t's. And so I now have equations for the x and the y, so I can summarize that my parametric equation is 3 plus t, comma, -1 plus 4t. We can also find a parametric of a circle. And for parametrics, the x value for a circle will always be r cos theta, and the y value will be r sine theta. So that's for a circle centered at 0, 0. If it turns out that it's not centered at 0, 0 and it's centered at maybe AB, then we just shift it over, r cos theta. So a plus r cos theta, and y will be b plus r sine theta. So that will center a circle at AB with a radius of r. Let's take a look at another example of just sketching a parametric. And in this case, we're going to try to sketch the parametric equation with x value t squared plus 1 and the y value t cubed minus 4t. So we build our table of values. I need some t values, I need some x values, and some y values. So, maybe start at 0. What's happening at 0 is y is 1 and x is 0. And then I can try what's happening at, say, plus 1. And I would get -2 and 3. Maybe I want to see what's happening at -1 as well, which is, sorry, this should be +2. This is +2 and -3. I can try +2 and -2. I can try maybe some values that are just kind of in between, -2.5 and +2.5. This turns out to give me 5, 0 and 5, 0. And these give me 7 1/4. And the negative value gives me 5.625. The positive value gives me -5.625. So you can double check this if you want, but there's no need. And then I have my Cartesian plane. And what I notice, let's start at the lowest t value, is my x value is 7.25 and my y value, I think this is switched around. I think this is negative and this is positive. So we get a point down here. So this is 7.25 and -5.625. And then the next coordinate that I get at -2 turns out to be at 5, 0, which is up here. So this is a coordinate of 5. So I know that my path is coming up this way. So I'll draw it here. And then at -1, it's at 2, sorry, these are backwards. This should be +3 and 0. So it ends up here. And then at 0, it becomes 1. And this actually does this kind of cool loop and then continues out this way. So this is the path now that I get through time. We'll take a look at another example. This is a special shape called a cycloid. And a cycloid is like a path that kind of bounces along the axes here with radius r. And it always has an x function that is rt minus r sine t, and a y function that is r minus r cos t. And what's actually neat about this is we can actually find the slope of the tangent. So if you've got a point on here and you want to know what the tangent line is, we can do that. So let's go back to the question that we had before. And so given that same parametric equation that we had before, let's find the tangent line at 3. So we had this shape, and at 3, what we can do is we can find its slope just by trying to find dy dt. But dy dt for our equation for this has two different parts to it. It's got its y value component, and it's got its x value component. So we need to do y prime, and we need to compare it to x prime. And so if I do this, then the derivative of the y component is 3t squared minus 4, and the derivative of the x component is 2t. And now I can simply say, well, what is that evaluated when t is 3? And so I get 23/6. And then, well, where is that? Where is the location at C3? Well, just simply putting it back into the original equation, I can find out that we're at the location 1015, and therefore I can get the tangent line equation. I'll just put it in point slope form for you. So y minus 15 and then x minus 10 with a slope of 23/6. So we can actually start to do some derivatives and integration types of technique with these parametrics as well. And we'll see more of this later on.